Hello, we're going to discuss chapter 7, section 8. So we deal with improper integrals. Under improper integrals, we have two types. We have type 1 and type 2. So let's start with improper integrals type 1. So improper integral type 1 is of this form. We have three cases under type 1. The first case is that we're going to integrate from a to infinity the function f of x. So here for case 1, the upper limit of integration is infinity. The lower limit is a number. For case 2 under type 1, the upper limit of integration is a number and the lower limit of integration is negative infinity. So we're going to integrate from negative infinity to a the function f of x. And then case 3 under type 1 is that the lower limit is negative infinity and the upper limit of integration is infinity. So we're going to be integrating from negative infinity to infinity the function f of x. So how do we integrate? So for case 1, you must change this improper integral. They call it the improper integral because of the presence of infinity and negative infinity. It's part of the limit of integration. So to do case 1, to integrate from a to infinity the function f of x, we'll have to change this improper integral to be the limit. So we will go where infinity is. We're going to replace infinity by t. And then take the limit as t approaches infinity of the integral from a to t of f of x dx. So basically, when you take this integral, when you take this limit as t approaches infinity, you can apply directly the limit to t, so that the limit as t approaches infinity of t is infinity. So then you go back to the original improper integral. So to solve case 1, first you change the given integral, improper integral, as a limit. And then you do the integral. When you're done, then you apply the limit as t approaches infinity. Then you get the answer. For case 2, you do the same thing. You replace negative infinity by t, and then you let the limit as a t approaches negative infinity of this integral from t to a of f of x dx. For case 3, so case 3, basically the first thing to do is to split case 3 into two integrals. So when you integrate from negative infinity to infinity, you can integrate from negative infinity to some number a, and then another integral is going to be, you're going to start from a to infinity. So you split one integral to two integrals. But that brings us, this is case 2, as you remember. You can see this, case 2, and this is case 1. So case 3 is basically case 2 plus case 1. So when you do case 1 and case 2, then case 3 is basically, there's nothing to learn about case 3, because what we're doing is we're doing case 2 and then case 1 at the same time. Okay, so let's go to an example. Evaluate the integral, improper integrals. So they give us, this is case 1. You have the integral from 1 to infinity of 1 over x squared dx. So so this is a is 1, and then infinity is the upper limit of integration. So to do this, we'll have to switch this improper integral into a limit. So the switch is okay. Just go where infinity is, replace it with t, and then apply the limit as t approaches infinity. And then to continue the integration, we will keep the limit. We will just integrate. We will treat this as if it was a regular integral. So we're integrating 1 over x squared. We know to integrate 1 over x squared, we have to change 1 over x squared as x raised to negative 2. And then use the power rule of integration we get x raised to negative 2 plus 1 over negative 2 plus 1. Then we can evaluate this as the limits of integration. We have 1 and t. So x equals t, x equals 1. So first we plug in t for x. And then when you plug in t for x, you get negative 1 over t minus. You plug in 1 for x, you get negative 1 over 1. And you end up with negative 1 over t plus 1, because negative 2 double negative makes a positive 1. You're still carrying the limits with you. At this point, then you can take the limit, because you're done with the integral. So you apply the limit you take the limit as t approaches infinity of negative 1 over t, plus the limit of 1 as t approaches infinity. We know by definition the limit of a constant is a constant, so the limit of 1 is 1. Here, when t goes to infinity, you're going to have negative 1 over infinity, which is 0. So for this integral, you get to 1. Anytime your integral improper integral gives you a finite number, then you say that improper integral converges. If your answer is infinity or negative infinity, then you say the improper integral diverges. Because 1 is a finite number, we say this improper integral converges. So I kind of said it here. So to go to case 2, now we have the lower limit, which is below. It's negative infinity. The upper limit is a number. So we're integrating e to the negative 2z. Again, we change this limit, this integral as a limit. We go to negative infinity, we replace it with t, and then we let the limit as t approaches negative infinity of this new integral, which is the integral from t to negative infinity of e to the negative 2z dz. Now, how do you integrate e to the negative 2 dz? We know by definition, if you have the integral of a, e to the ax dx, the answer is e to the ax over a. So in our case, when you integrate e to the negative 2 dz, the answer is going to be e to the negative 2 dz over negative 2. And then we're going to evaluate this at the limit of integration. So z equals t, and the z equals negative 1. So we plug in negative 1 for z into here, minus, and then we plug in a t for z into the answer. And double negative makes it positive, and double negative here makes it positive. So we get e squared over negative 2 plus e to the negative 2t over 2. We keep bringing the limit down with us, and then at this point we can take the limit. Because we're done integrating, we evaluated the integral with those boundaries. So we take the limit as t approaches negative infinity of e to e squared over 2, but this is a number. So the limit of a number is a number. You get e squared over negative 2. When you take the limit as a t approaches negative infinity of e to the negative 2t over 2, we can go and plug in negative infinity for t. So which give us negative 2 e to the negative 2 times negative infinity, which makes it positive 2 times infinity, which is positive infinity. So you get e to the infinity over 2, which is infinity. Infinity plus a finite number is infinity. So because the answer is infinity, we say the integral diverges. For the last case, case 3, we have the integral from negative infinity to infinity of x squared over 16 plus x to 6 dx. So with case 3, we have to split this case 3 into case 2 and case 1. So you pick a number between negative infinity and infinity. I pick 0. You can pick any number. You can pick 2, you can pick 3, you can pick 1. So I pick 0. So that means I can split this integral from negative infinity to 0 plus the other integral from 0 to infinity of the same integrand. So this, I know this is case 2 and this is case 1. So I call the case 1 as I1, and then I call case 2 as I2. So I'm going to start with case 1, so I1, this integral. So the integral from 0 to infinity of x squared over 16 plus x to the 6 dx. To solve it, I will rewrite x to the 6 as x cubed squared. Then I can use u equals x cubed as the u substitution. and then a du is going to be 3x squared dx. Since I have x squared dx here, I can solve this equation. I can divide this equation by 3. I get a d over 3 equals x squared dx. Then I can change limit of integration. When x is 0, u is 0 because you got 0 cubed is u is 0. When x is infinity, you get infinity cube, which is infinity. U is infinity. So we still have the same limit of integration, 0 to infinity, of 1 over 16 plus, this is u squared, and then a dx squared dx is a du over 3. So I bring 1/3 outside, and then I'm going to integrate from 0 to infinity, 1 over 1, 16 plus u squared du. I know this integral basically very well. It's going to give me 1 over 4 times arctangent of u over 4. Then I'm going to evaluate at 0 and infinity. So I multiply these two numbers, I get 1 over 12. And then here, I evaluate this at infinity, I get infinity over 4. I plug in 0 for u, I get 0 over 4. Infinity over 4 is infinity. 0 over 4 is 0. So I get arctangent of infinity, which is pi over 2. And then arctangent of 0 is 0. So I end up with 1 over 12 times pi over 2, which is 1 over 24. So I1 give me pi over 24. I2, which is negative infinity, the integral from negative infinity to 0 of x squared over 16 plus x to 6 dx. Again, I did the same thing. Okay, so until I let u be x cubed, and again, I get this integral. Then I'm going to evaluate at negative infinity and 0. So when I plug in 0, I get arctangent of 0, which gives me 0. And then when I plug in infinity for u, I get arctangent of negative infinity, which is negative pi over 2. So I will get 0, double negative, negative and negative makes it positive pi over 2, times 1 over 12, give me pi over 12. I mean pi over 24. So therefore, the original integral, the integral from negative infinity to infinity of x squared over 16 plus x to 6 dx is I2 plus I1. I2 is pi over 24 plus I1 is pi over 24, which gives me the final answer pi over 12. Okay, so these are the three cases. Thank you.